Okay, hello everyone. This is going to be a walkthrough of the first question on the week 7 worksheet, okay? So asymptotic lists. Given a linked list of length n, give a tight asymptotic runtime bound for each operation. Recall that int list is a naive linked list that only keeps track of the start node. SL list is an encapsulated singly linked list with a front sentinel, and DL list is an encapsulated doubly linked list with both front and back pointers. So let us quickly remind ourselves about what bounds we have to work with here. Okay, we have omega, which is our upper bound. Sorry, O, I'm sorry, that's an O. Omega, which is our lower bound. And we have theta, which is our tight bound. And theta only exists when the tightest big O and the tightest big omega converge to the same value. Okay, so with that in mind, let us get started. Let's start by thinking about size. So really quickly, if I look into the SL list class and the DL list class, I can see that they both have int size. They both contain the size as an integer. Now, int list doesn't have, it's not keeping track of the size, right? So that means if I want to figure out the size of int list, I have to do it manually, right? I have to actually go in and take a look at what there is inside of the int list and count, and that's the only way for me to figure out the size. So that's going to involve traversing the entire int list. And that's going to be theta of n, right? Theta because it's always going to take me the same amount of time to work my way through the int list, and n because I'm going to have to pass through n things, okay? Now, how about SL list and DL list? Well, because we have this, the size is being kept track of, this is just going to be a constant. This is going to be theta of 1 for SL list and DL list, okay? I don't have to do any traversing. Now, how about get? Okay, so here's the thing about get. It's going to really depend on, what I'm trying to get, right? If I'm trying to get the very first thing, then that's going to be just theta of 1. The worst situation that I could have would be where I have to get the very last thing, right? Which is going to be theta of n. So we can think back to how we discussed, using best and worst case to find tight bounds for the average case. So I'm going to use the fact that the worst case would be theta of n to give a tight upper bound for getting. Okay? Now, how about add first? Well, add first is always going to take me the same amount of time. It's just going to be theta of 1, right? It doesn't matter if I have a int list, SL list, DL list. This is just theta of 1. But add last. Well, for int list and SL list, I'm going to have to make my way through the entire int list, the entire SL list, and then tack on something at the very end, right? So that means that adding last is always going to take me theta of n time for an int list and an SL list. Now, a DL list is different. A DL list is going to take me theta of 1 time because I am keeping track of that tail. Okay, so it's just going to take me constant time to add something into the end if I have a DL list. Okay, how about add before? So when we're doing add before in the context of int list and SL list, we have to iterate through the list from the start to find the node before the current node. So that means that it's going to take us well, the upper bound on adding before is going to be big O of n. Now, how about if we have a DL list and we try to do add before? Well, we can look over here in the DL class and remind ourselves that DL list has a pointer from each node to the next node and to the previous node. So that means that adding before is going to be constant time. We don't have to iterate through the entire list like we would have to in the context of int list or SL list. Now, how about add after? Well, we can see that in the case of int list, SL list, DL list, all of these structures have access to node n's next pointer. So for all of these lists, it's going to take us theta of 1 time to add after. Okay, what's going to happen when I try to remove? So if I'm given an index and I'm trying to remove something based on an index, the first thing that I have to do is I have to make my way over to that index and then make adjustments. So the thing that's going to be taking time here is essentially you can almost think of it like it's similar to get, right? I have to make my way over to that index before I'm making adjustments. And in all structures, that's going to take me big O of n time. So how about if I'm given a node? Okay, so in the case of DL list, the doubly linked list, it has a pointer to the previous node and to the next node. Okay, so it can remove the node and point to the next node based on this input without having to go through the entire list and to figure out which node is before the current node, right? With S list and with int list, they don't have that that pointer that's pointing to the previous node. So their only option is to go through the entire list and find that out manually. Okay, so that's going to take O of n time for int list and SL list, but for DL list, it's only going to take theta of 1 time because of that extra bit of information that's contained within the the doubly linked list. Okay, so I know that I did a video about an introduction to asymptotics, but I don't think that I discussed these sums. So I'm just going to do that really quickly right now for you guys so that this is cleared up. So we just want to be sure that we recognize arithmetic and geometric sums. Okay, so when we have an arithmetic sum, that means that the difference between consecutive elements is constant. 1 plus 2 plus 3, 5 plus 10 plus 15. The runtime that we want to be associating with this type of sum is theta of the last term squared. Okay, so for these right here, these would be theta of n squared. Now, a geometric sum is when the ratio of consecutive elements is consistent. In other words, you're routinely multiplying by something, right? This is multiplied by 2, by 2, by 2. You know what I mean? So when we see a geometric sum, we want to be thinking of the fact that this runtime is going to be theta of the last term, okay? So for example, these ones are going to end up having theta of n as their runtime, okay? Okay, let's do 1.2 part A. We add a method, add all to the int list, SL list, and DL list classes, assuming no elements have been inserted before this method is called, and add all's implementation repeatedly calls add last. Give the runtime of add all in terms of n, the size of the collection C. So I have just put out this pseudocode here. I don't know if this is helpful to anybody, but it's generally pretty helpful to me just to, orient myself. It's nice to have some pseudocode. So now we're gonna do this, okay? I actually am gonna say, let's start with DL list. So when I do add last for a DL list, what's the runtime of doing that? Well, it's going to be theta of 1, right? Because I have that I'm keeping track of the tail in a DL list. So it's going to take me constant time in all cases to add last for a DL list. Now, if I have to add last n times, and it's always taking me theta of 1 time, then I'm just going to end up with something that takes me theta of n time, right? Because if I have this collection like this, then this is theta of 1, however many times, right? It's going to end up being theta of n to do all of them. Okay. Now, how about int list and SL list? Well, it's different for these ones, for int list and SL list, okay? Recall that adding last for an int list or an SL list, that takes theta of n time for those guys. So let's just say, so add last is theta of n. But n, in this add last, when we say theta of n, we mean n is the size of the current list, okay? So let's just do this out as an example, and let's just find out what the runtime is going to be. So let's say that this is my collection right here, and we're starting off with nothing in our list, okay? So if I want to add last 1, right? That didn't take me any time. Now, what if I want to add last 2? Well, at this point now, I'm starting to get to the situation where I need to iterate. So I need to iterate from the first one to the second one. So that took me 1. We can say that that was 1. Now, what if I want to add last 3? Well, at this point, I'm just going to have to iterate even more, right? I have to start from 1, and I have to go to 2, and I have to go from 2 to 3. So that's plus 2. And this is going to continue. This pattern is going to continue, and it's going to continue all the way up until n minus 1, right? Until we have added every single item from the collection. So what is this sum? Well, this is a sum that we should recognize immediately, right? This is one of those really important sums when we're doing asymptotic analysis. The thing to realize is that this is theta of n squared, okay? The arithmetic sum 0 plus 1 plus 2 plus da 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 da. We need to be thinking theta of n squared whenever we see that sum, okay? So that's why int list and SL list are going to end up being theta of n squared. Okay, can we re-implement add all to improve its runtime? What is the new runtime for int list, SL list, and DL list? Okay, so let's think about what we had going on in add all for int list and SL list. I mean, DL list, it was pretty good, right? It was theta of n. It's not really going to get too much better than that. So let's see if we can improve int list and SL list. What was it that was just ruining our runtime for int list and SL list? Well, it was the fact that whenever we did add last, we had to iterate through the entire list for int list and S list, right? And that just ended up giving us just a terrible runtime for adding all. So DL list was so much better because it was keeping track of last node, right? So that gave us a very easy way to just insert something at the end. So how about in our new implementation, we kind of throw out the whole, call to add last in the case of int list and SL list, and we instead just start keeping track of the last node. So in that sense, we just have to basically append to the end for int list and SL list instead of doing a call to add last. And then we know that this, if we're keeping track of the end, well, this is going to take theta of 1 time. And if we have to do this, Sorry that I kind of didn't really, I should have put this. This is just some pseudocode to help us figure this out, okay? If I have to append to the end for all X in the collection, and we know that there were N of them, right? Then this is gonna end up being basically exactly the same as DL list, right? I do something that takes me constant time N times, and I end up with a runtime that is theta of N, okay? So we improved the runtime for int list and SL list.